The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you would have seen the last organic chemistry class, that is haloalkanes and haloarenes. Don't find it difficult, because if you do it with passion, if you understand the concept and do it, definitely it is going to be easy for you. So now we are getting into the next chapter, that is alcohol, phenols and ethers. From 10th standard, 11th standard, we have been hearing alcohols and phenols, right? Even ethers in 10th standard, we were just doing the name, that is IUPAC names. If you remember the functional group alkoxy. So this year, we are going to study how it is prepared, how do we name them, and what are the properties or what are the characteristic features of these compounds. To start with alcohols and phenols, alcohols and phenols are formed when a hydrogen atom in a hydrocarbon, which is aliphatic or aromatic, is replaced by OH group. So we know alkane, that is when I take ethane, it is CH3CH3. If one of the hydrogen is replaced by an OH group, you call it as an alcohol. If you can recollect what we learnt last year, children, you can just understand better. An alcohol contains one or more hydroxyl groups directly attached to the carbon atoms of an aliphatic system. If it is an alcohol, definitely OH group is being attached to the carbon atom in an aliphatic compound. If it is a phenol, the OH group is attached to the carbon atom of an aromatic system. We have a difference between aliphatic and aromatic. In aliphatic, you know what are the hydrocarbons we have. In aromatic, we know what are the hydrocarbons we have. So these are alcohols and phenols. Now, the substitution of a hydrogen atom, when a hydrogen atom is replaced by an alkoxy group or aryloxy group, you call it as ethers. You remember, children, CH3, one of CH4, or when I say CH3, one of the hydrogen is replaced by an OR or O aromatic group, you call it as ethers, or you also call it as alkoxy alkane. Example you have here, OR is a functional group. I have 2 methyl, so I call it as dimethyl ether, or I call it as methoxymethane. You remember, children, these are the things that we learnt in the last years. So now we will learn something important about the chemistry of these 3 classes of compounds, alcohols, phenols and ethers. First, let us learn the classification. Alcohols and phenols may be classified as mono, di, tri or polyhydroxy compounds depending on how many OH groups are present. Depending on the number of hydroxyl group present in the compound, they are classified as mono, di, tri or polyhydric. Now let us see, here we have only one OH, so this is called as monohydric. I have 2 OH, so it is called as dihydric. Here I have 3 OH, so I call it as trihydric. Monohydric alcohols may be further classified depending on the hybridization. Compounds containing CsP3 bond. When I say even in haloalkanes and haloarenes, we were talking about the type of hybridization that is there for the carbon in which the functional group is attached. So in this, if the OH group is attached to sp3 hybridized carbon atom, then you have three types mainly: primary, secondary, tertiary, which we have already seen in haloalkanes. You remember? If the halogen atom is attached to only one carbon atom, it is primary. So similarly here, if the hydroxy group is attached to only one main carbon atom, it is primary. Here the carbon atom which is holding the OH is attached to two carbon atoms, so it is secondary. Here the carbon atom is attached to three main groups, so you call it as tertiary. So after this CP3, we have in that one more branch which we call it as allylic. Remember allylic, haloalkane children? Yes. OH group is attached to sp3 carbon which is adjacent to the carbon-carbon double bond. It is not directly attached to the carbon-carbon double bond, but it is adjacent. If you see the example here, OH attached to the carbon atom which is attached to the carbon that is doubly bonded. Not this carbon is double bond, but the carbon which is holding the OH is attached to the adjacent carbon which is double bond. If you see here, this is primary because it has only one carbon that is double bond. Here C is holding the OH which is attached to two carbon atoms. Here C is attached to OH which is attached to three carbon atoms. So you call it as primary, secondary and tertiary. Now we will see what are benzylic alcohol. From the name it is very clear, there is a benzene ring. OH group attached to sp3 hybridized carbon atom which is next to the aromatic ring. So if you see the structure here, you can very well understand OH is attached to the carbon atom which is attached to the benzene ring. OH is attached to carbon atom which is holding my benzene ring. Again, which is holding my benzene ring. Here this carbon which is holding the OH is attached to only one C. Here it is attached to two carbon atoms. Here three carbon atoms. That is why we have primary, secondary and tertiary. Next is compounds containing CsP2OH bond, where the carbon is sp2 hybridized. The OH which is attached to the carbon is sp2 hybridized, where the carbon which is holding the OH is doubly bonded. So that is called as vinylic. In allylic, carbon that is holding the OH is attached to the adjacent carbon that is doubly bonded. Here the carbon that is holding the OH is only doubly bonded, such that is OH attached to the carbon which is having a double bond. Such a structure we call it as vinylic alcohol or vinylic structure. So next we have phenols. So these are nothing but a group which we call it as phenols. Monohydric, where here also monohydric, 2OH dihydric. When you have 3OH, you call it as trihydric. Next, ethers. Ethers are classified as simple or symmetrical. If the alkyl or the aryl groups attached to the oxygen atom are the same, both the side if you have the same, you call it as symmetric, or and mixed or unsymmetrical if it is different. That is, if you have this structure C2O5, C2H5O, C2H5, both the side of the oxygen you have the symmetrical group, same alkyl groups. So you call it as symmetrical ether. But if you have different alkyl groups, you call it as unsymmetrical ethers. Say here you have phenyl group, here it is ethyl group, again it is unsymmetrical. So ethers are classified as symmetrical or unsymmetrical depending on the alkyl or the aryl groups that are present on both the sides of oxygen. Nomenclature, you know, we have already done in 11th standard, even in 10th standard, where the alkane E is being replaced by OL, and depending on the number of OH groups, we add this di, tri and polyhydric alcohols. So you have different examples in your textbook. We have also a group of compounds which are called as cyclic alcohols, that is no double bonds inside the benzene ring. So this is cyclohexanol because 6 carbon atoms are present. Here 5 carbon atoms, the carbon holding the OH will be given the position number 1. So it is 2-methyl cyclopentanol. Okay. Some of the examples, please look at your textbook and learn, children. And for ethers, you know how we do the alphabetical order, right? So now we'll get back into the structure, which is the most important. When I compare the three structure, alcohol, methanol and ether, what do we observe is, in alcohol, this is my alcohol CH3OH, the oxygen of the OH bond, this oxygen of this OH bond is attached to the carbon by a sigma bond. It is using a sigma bond by an overlap of the sp3 hybridized orbital of carbon with a sp3 hybridized orbital of oxygen. Both carbon and oxygen, the sp3 hybridized orbital will be overlapping in the case of alcohol. Now you can see here. Now let us see what is the bond angle. The bond angle of alcohol COH is less than the tetrahedral, which is 109 in tetrahedral. Now why it is less? Because of the repulsion between the unshared electron pairs of oxygen. In the oxygen is having an unshared electron pair which is having a repulsion, so the bond angle becomes less when compared to the tetrahedral structure. But what is the case in phenol? The OH group is attached to sp2 hybridized carbon atom of an aromatic ring. The carbon oxygen bond is less than that of methanol. Compared to that of alcohol, the carbon oxygen bond is actually less in case of phenol due to the partial double bond character. You know, I have shown you in 11th standard that the double bond can move. You can write in both the resonance structure of benzene. So there is a conjugation of the double bond of an electron pair and there is an unshared electron pair of the oxygen in the aromatic ring. But what happens in case of ethers? The two bond pairs and the two lone pairs of electrons on oxygen are arranged approximately in a tetrahedral arrangement. So the bond angle is actually greater when compared to that of alcohol and phenol due to the repulsive interaction between the alkyl groups. You have both the side bulky groups which actually repel. Because of that, the bond angle is actually bigger when compared to that of alcohol and phenol. Now we will learn about the preparation of alcohols. Okay. Sorry, I was just turning around. Now we will get into the preparation. First preparation is from alkenes by acid catalyzed hydration. What is acid catalyzed? I am going to use an acid as a catalyst. And what is hydration? We know hydration means addition of water molecules. So alkenes react with water in the presence of acid as catalyst to form alcohols. What is happening here? This is my alkene. When it reacts with water in presence of acid, which we denote it as H+, you get hydrogen attached to one carbon, OH is getting attached to another carbon atom. This is with symmetrical alkenes, both the side having the same groups. When I have unsymmetrical alkenes, the addition takes place according to Markovnikov rule. What is Markovnikov rule? The negative part will get into the carbon which is having less hydrogen atoms. So remember that rule when you are doing with unsymmetrical alkenes. Now let us see how does this mechanism work out. Now first and the foremost step is the protonation of alkene to form carbocation. So I have my alkene here. Now listen carefully, children. This is H2O, this is H+, that is my acid. Now what is happening here? This carbon attacks my hydrogen, the bond gets shifted inside. So what happens? Because of this removal of a single bond, this becomes less in its valency. So there becomes a carbocation with the removal of water molecule. The second step is the nucleophilic attack. So there is a lone pair of electrons which comes and attack my carbocation which is electron deficient. When it comes and attacks, it becomes OH2. What is the third step? The easiest step, where again it reacts with water, where this negative part comes and attacks my hydrogen. So this bond gets shifted, hydrogen is removed as H3O plus hydronium ion and OH comes and attacks the carbon. So you get your alcohol. So this is how alcohol is being formed. The second reaction is again an easy reaction, which is called as hydroboration oxidation. That is diborane, which is nothing but B2H6. It reacts with alkenes to give trialkyl boranes as addition product. This is oxidized by hydrogen peroxide in the presence of aqueous sodium hydroxide. What is actually happening in the reaction? If you see, this is propene which reacts with diborane. You get here hydrogen comes in attacking, BH2 comes in attacking our, that is a bond gets break. Both the carbon is being given substituted by one by hydrogen and one by BH2. Again, when this molecule reacts with propene, you get twice of the propene molecule with BH. That is BH2 becomes BH. See what is happening in the B. The number of hydrogen gets actually removed. So this again on reacting with propene, you get thrice of propene molecule with B, which on reacting with sodium hydroxide, you get OH comes and attacking with BOH thrice, which is again as a byproduct. This is a very important reaction, that is number of hydrogen gets removed here, it becomes BH2, BH and B. And last, when you treat with sodium hydroxide, you get your alcohol which is being formed. The addition of borane to the double bond takes place in such a manner that boron atoms gets attached to sp2 carbon, which is carrying more number of hydrogen atoms, not the Markovnik. In Markovnikov rule, less number of hydrogen atoms, here with more number of hydrogen atoms. The next reaction is very simple, which is from carbonyl compounds. First one is reduction of aldehydes and ketones. We know what is an aldehyde, which has got a CHO group. What is a ketone? Which has got a CO group. Catalyst is finely divided metal like platinum, palladium or nickel. How it is prepared? Aldehydes and ketones can react with hydrogen in presence of any reducing agent. I can use sodium borohydride as my reducing agent. I can use lithium aluminium hydride. These are strong reducing agents which will give my alcohols. And always remember, aldehydes give primary alcohols, ketones give secondary alcohols. This is a very important question, how to prepare alcohols from carbonyl compounds. When I say carbonyl compounds, definitely carboxylic acids and esters also comes. Carboxylic acids are reduced to primary alcohol by using a very strong reducing agent like lithium aluminium hydride, where the COOH group is being reduced to CH2OH by using lithium aluminium hydride. It's a 1 mark question. But since this is very expensive, what do? We convert alcohol, that is acid. When it treats with alcohol, you get an ester. You remember this, we studied in 10th standard, esterification. Acid, when treats with alcohol, you get an ester, which on reduction with hydrogen and using a catalyst, it undergoes catalytic hydrogenation, that is removal of oxygen and addition of hydrogen, where you get your primary alcohol. I repeat, acid with alcohol will give an ester, which on reduction will give alcohol. Okay, two types of alcohol is what you are getting. Okay, next is from Grignard reagent. Remember our MgX children, we learnt in the last class, that is the last chapter. Alcohols are produced by reaction with Grignard reagent. What is actually happening? It's a very simple reaction. You just have to understand the mechanism. This is my ketone or my aldehyde, which when treated with RMgX, if you see, this gets split. RMgX gets split into two parts. The R part comes and attacks my carbon. So I get R here, which is attached. Now oxygen is negative. So oxygen will attract my magnesium. So I get OMgX. Understood? Which on hydrolysis, this breaks up. So you get here this C, this OH, that is Mg breaks. So you get your hydrogen coming here, OH going here. H2O breaks as H plus and OH minus. H comes and attacks with oxygen. OH goes into my MgX part. So, you get MgOHX. Examples you can see aldehyde with RMgX, RCH2O MgX, RCH2OH MgOHX. Similarly with ketone. So, this is again an important, don't think why teacher says every reaction is important. When organic chemistry is concerned, every reaction has its own value. So, you have to learn it. Okay children. Of phenols from haloarenes, benzene sulfonic acid and diazonium salts. This we have already learned the other way. If you remember the properties we learnt of haloarenes. Chlorobenzene, when it is fused with sodium hydroxide at 623 Kelvin, you get the sodium salt of phenol, which is again treated with HCl, an acid catalyst. Then you get your phenol. Sodium combines with chlorine to form NaCl. The hydrogen comes and attacks the oxygen. The next reaction is from benzene sulfonic acid. How do we get it? Benzene, on treatment with oleum, you get benzene sulfonic acid, which again when treated with combination of NaOH and HCl, you get your phenol. So, if you learn the first reaction, slowly you can learn your second reaction as well. The next one is with diazonium salt, Sandmeyer's reaction. Remember children, aniline, when it is treated with sodium nitrite and HCl, you get N2Cl, but there we were using Cu2Cl2 and Cu2Br2, remember, or Ki for iodine. Here just warming and hydrolyzing you get your phenol. So, same diazonium salt, when treated with water and warming you get your phenol. Next one is a very important reaction from cumene. That is, phenol is manufactured from the hydrocarbon, that is cumene. This is my cumene. What is cumene? Which is isopropyl benzene. This is CH, CH3, CH3, two side you have the same groups. So, you call it as isopropyl, which is attached to my benzene ring, which on oxidation, this parts break, the CH part break, you get COOH, cumene hydroperoxide, which on treatment with water and also by treatment with H plus you get your phenol and acetone as a byproduct. Very, very, very important reaction as of preparation of phenol is concerned. Next one is physical properties. Again, you know, the most important is the boiling point of alcohol and phenol. They increase with the addition of number of carbon atoms. Actually, the boiling point decrease with increase in the branching. When the carbon atom branches increases, the boiling point actually decreases. And if you see the hydrogen bonding presence in alcohol and phenol, okay, when compared to that of other class of compounds, namely like hydrocarbons, ethers or haloalkanes, definitely ethane and propane, if you see the boiling point is very high when compared to alcohols as that of alkanes and ethers, because of just intermolecular hydrogen bonding that is present in alcohols and phenols. Okay. Solubility, if you see, they are highly soluble because of the forming of hydrogen bonds with the water molecules. Okay. So, you can just go through all those. The next we will learn about the chemical reactions and then we will get back into. Yes children. Now, we are going to see about the chemical reactions that are involved in alcohols and phenols. Now, if you see, alcohols are versatile compounds. What do you mean by versatile compounds? They are really different because they can react both as nucleophiles and electrophiles. The bond between, now we know ROH, that is CH3 CH2OH. In this, if the OH bond is broken, then we call that as a nucleophile, right? But if the CO bond is broken, then they will act as an electrophile. This is how this alcohol can act as both nucleophile and electrophile. Now, let us see how does it work. This is my alcohol, in which this is another compound. When this oxygen having an unshared pair of electrons attacks the carbon atom, you get, which is being connected here, ROH connected to C, and you get the hydrogen, that is the OH bond being broken, and you get RO and whatever is the reactant molecule. So this OH bond, when it is broken, this will be serving as a nucleophile where it looks for an electron deficient center. Similarly, when the CO bond is broken, it acts as an electrophile. Now how does it work? We know R CH2OH plus H plus. Now the CO bond should be broken. So when this attacks, you get CH2ROH2, and when a nucleophile comes and attacks, this bond will be broken. So you get CH2RBr with removal of oxygen. So that is how this alcohol will be acting as both electrophile and nucleophile. So based on this cleavage, we will be seeing how does the reaction occurs. Now the first one is reactions involving the cleavage of OH bond. Now in this, only the OH bond is being cleaved, means it is broken. Now the first one is when it reacts with metals. When it reacts with metals like sodium or potassium or aluminium, you get the corresponding alkoxide, that is sodium alkoxide, potassium alkoxide, aluminium alkoxide. So how does it work actually? We know this OH bond has to be broken, so the H will be removed, and when H comes out, this whatever is a metal that it is reacting will be connected to the alkyl. So this is how when alcohol reacts with metals, you get the following product. Now what is the case when phenol reacts? When phenol reacts with sodium, you get sodium phenoxide, that is H will be removed as hydrogen gas, and this sodium comes and attacks the oxygen. So that is how you get it. Right. Now not only sodium, when it reacts with a base like potassium hydroxide or sodium hydroxide, you get the same byproduct, that is sodium phenoxide, or I will say metal alkoxide. Now these reactions show that alcohols and phenols are acidic in nature, because you know what is an acid? An acid should be a proton donor. And in fact, we know these both are Bronsted acid because they can easily donate a proton. An hydrogen atom or hydrogen ion is being donated very easily. So with which we get this base, when it reacts with an alcohol, hydrogen is removed, which is getting connected with a base, and you get a here RO, which is called as a conjugate base and a conjugate acid. An acid becomes a conjugate base, a base becomes a conjugate acid. Now to check the acidity of alcohols, which is very important, the acidic character is due to the polar nature of OH. We have studied the polarity. How do you say this compound is polar? When there is a development of the partial negative or the positive charges. So an electron releasing group increases the electron density on oxygen. This is my oxygen, these are my electron releasing group. I can see R written, which can be my methyl, ethyl, propyl, butyl, etc. So these electron releasing group, they increase the electron density on oxygen, which will decrease the polarity of oxygen. So what does it mean? As the number of electron releasing group increases, the polarity of the OH bond actually decreases, because the electron density also decreases. So increases. So we will say primary is more acidic than secondary, which is more acidic than tertiary. So when compared to primary, secondary and tertiary, primary alcohols are more acidic in nature. That's a very important question again. Now alcohols, however, are weaker acids than water. Alcohol are good acids, I told you, because they are proton donors, but compared to water, they are little bit weak, because water can immediately donate a proton much better when compared to that of an alcohol. So that's why we say water is more acidic than alcohol. Now alcohols also acts as bases, not only as acids but also bases, because they have an unshared electron pair on the oxygen. We know ROH, hydrogen can also be donated, oxygen is also having a pair of electrons, so they also act as a base, which make them proton acceptors. So they are very easily can accept a proton. Now when we study about alcohols, should we not study about phenols? Let's see what is the acidity of phenol. The reaction of phenol with metals show that they are acidic in nature. right children, because we have studied that metals react with HCl giving hydrogen gas, or metals react with in 10th standard you have studied magnesium plus HCl, aluminium plus HCl and all giving hydrogen gases. Now the hydroxyl group in phenol, this is OH, in phenol is directly attached to the sp2 carbon, because we know in benzene carbon is sp2, but in aliphatic alcohols it is sp3. So this is sp2 which acts as an electron withdrawing group. What does this benzene acts as? An electron withdrawing group, and we know oxygen has got a pair of electrons, so those electrons will be accepted or withdrawn from the oxygen towards the benzene ring. Now due to this charge distribution, this resonance structure we have studied last year also children, these two pair of electrons when it comes attracted by the benzene ring, there will be a double bond. Immediately when there is a double bond, you cannot have adjacent two double bonds. So one of the double bond comes out, bears a negative charge. Again this keeps on moving where you have a plus charge here because of the valency not being satisfied. So the reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acids than alcohols only because of the reason that they have resonance structure and the charge is being everywhere, it is being delocalized over the complete ring, right? See, in which the hydroxyl group attached to the aromatic ring is more acidic than the one which is attached to the alkyl group, just for a simple reason that aromatic ring, or I can say benzene ring, carbon is sp2 hybridized. So what happens, the electrons get delocalized, and being an electron withdrawing group, this becomes more stable, and that's why they are more acidic as compared to that of my alcohol. So if you see the reactions here, ionization of alcohol giving RO minus and H plus, but this is giving a phenoxide ion. This is alkoxide, this is phenoxide ion. But listen children, due to higher electronegativity of sp2 when compared to my R, phenol which OH is attached, electron density increases on oxygen. The electron density increases the polarity of OH bond and results in the ionization, which shows that which is more and more acidic as compared to that of my alcohol. But when phenol and phenoxide ion are compared, both are having resonance structure, but phenoxide ion becomes more and more stable as compared to that of phenol molecule, right? Because the charge separation is here, if you see there are two lone pair of electrons, but there you have only one lone pair of electrons and a positive charge here, and you have a negative charge here, right? And in substituted phenols where you have electron withdrawing group and electron releasing group, that enhances the acidic strength. When there is an electron withdrawing group, the acidic strength increases. Whenever there is an electron releasing group, the acidic strength decreases. This is most important. Okay, the second one is the esterification, where alcohols and phenols, they react with acids or acid chloride to form the esters. Here my AR represents phenol, aromatic ring, and ROH represents aliphatic. So when it reacts with a carboxylic acid, you get an ester form, right? It can be AROCOOR or it can be RCOOR. Okay, so it can be an aromatic ester or an aliphatic ester when it reacts with acid or acid anhydride or acid chloride. These are all carbonyl compounds. So if you want to prepare an ester from alcohol or phenol, you should make sure that they react with acid chloride or acid anhydride or carboxylic acid. Now this is carried out in the presence of small amount of concentrated sulfuric acid because the reaction can be reversible. So the reaction with acid chloride is carried out in the presence of a base. The first two reaction in presence of an acid, but this reaction is in the presence of a base because you have to neutralize the HCl which is formed during the reaction. When an alcohol or phenol reacts with an acid chloride, you get an ester and hydrochloric acid. Now this hydrochloric acid which is formed as a byproduct should be neutralized. Now how do we do neutralization reaction? Only when you react it with a base. So here we use pyridine which is a base. Okay. Now the introduction of acetyl group in alcohols or phenol is called as acetylation. So they can give you in the exam, write the acetylation reaction. So you should be knowing it. And the next reaction is the most important reaction, formation of aspirin, which is salicylic acid, acetyl salicylic acid. What happens here? This is my salicylic acid. You can see a benzene ring, OH phenol attached to a COOH, right? When it is treated with acetic anhydride, CH3CO twice O, this is acid anhydride. Please remember children, RCO, the whole bracket twice O, that is acid anhydride. In presence of an acid, you get OCOCH3 group attached. This group OCOCCH3. This hydrogen is being replaced by COCH3 plus you get an acid. Now this is called as aspirin. You know what is an aspirin? It is used in medication. Very important preparation of aspirin from salicylic acid. Next one is, till now we were seeing cleavage of OH bond. Now we will see cleavage of CO bond. First one is when it reacts with hydrogen halide. It can be HCl, HBr, HI. How does it happen? The difference in reactivity between the three alcohols, that is primary, secondary and tertiary, very important test to determine the difference in the primary, secondary, tertiary alcohol, which we call it as Lucas test. Now what happens here? When an alcohol reacts with HX in the presence of concentrated hydrochloric acid and zinc chloride, you get the corresponding halides formed, alkyl halides. Now see here, they are immiscible and produce turbidity. If it is a tertiary alcohol, the turbidity is produced immediately, and if it is a primary, it takes some time. Sorry, secondary, it takes some time. Primary, they do not form. This is a very important test for differentiating the primary, secondary and tertiary alcohol. I repeat, when alcohols react with HX, that is hydrogen halide, you get alkyl halides formed. In the product, when you get turbidity immediately, it is a tertiary alcohol. If it is formed little bit later, it is secondary. If there is no turbidity, it is a primary alcohol, and the test you call it as Lucas test. Next one is reaction with phosphorus trihalides. If you remember, we studied this for the preparation of haloalkanes. Alcohol plus PCl3 gives RCl plus POCl3. You remember children, we studied. So you should always remember the preparation of something will be the property of another compound. Next one is dehydration, which is removal of water molecule. Now alcohols, when it is heated, one molecule of water is removed. So when a molecule of water is removed, the single bond becomes a double bond. The opposite of it we studied in the preparation of alcohol. You remember children, from unsaturated hydrocarbon. Yes, alkenes on hydration gives alcohol. So what should happen? Alcohols on dehydration will give alkenes. So ethanol, when it is treated with sulfuric acid and heated at 443 Kelvin, you get a alkene, that is formation of double bond in the compound. Now how do secondary and tertiary alcohols react? Secondary alcohol gives again an alkene, tertiary also gives an alkene, but the temperature will be little bit different. So the reactivity is, tertiary will be more reactive towards the dehydration, then secondary, the least will be the primary. Mechanism you need not learn, just go through it, it is not that important. Now we will go to oxidation. What is oxidation? The bond breaks, a molecule of oxygen is being added. So what happens here? Cleavage happens with the formation of bonds that occur in the oxidation reaction. See here, most important reactions. Primary alcohol on oxidation gives aldehyde. Always we have studied this in the preparation of alcohol from carbonyl compounds. Aldehydes on reduction gives primary alcohols. Ketone on reduction gives secondary alcohol. So remember children, so the reverse is nothing but primary alcohol on oxidation gives aldehyde, which again gives an acid. We use strong oxidizing agents like potassium permanganate, chromic oxide. Okay. Now this primary alcohol which gives an aldehyde, you can also use PCC, that is pyridinium chlorochromate. It comes in 1 mark question. Secondary alcohol, when you treat with a strong oxidizing agent, you get a ketone. How do we say it is secondary? The OH carrying carbon is attached to my 2 alkyl groups. So primary is giving aldehyde, secondary is giving a ketone. What will happen to tertiary? Tertiary alcohols will never undergo oxidation. But under strong conditions like KMNO4, and when you use different temperatures or in the presence of copper or other compounds, it undergoes a slight cleavage with a less number of carboxylic acid. Now this is very important, where primary, secondary and tertiary alcohol, when it is treated with copper in 573 Kelvin temperature and the reagent are the same. Both, that is the primary, secondary, tertiary, when they are treated with copper at 573 Kelvin, primary gives an aldehyde, secondary gives a ketone, but tertiary gives an alkene. You don't get an aldehyde, ketone or acid. Instead, you get a double bonded compound which is an alkene. So this is called as dehydration. Dehydration in presence of copper at 573 Kelvin. Dehydrogenation actually takes place with the removal of hydrogen molecule. Next is reaction of phenols. See, phenols undergoes only electrophilic aromatic substitution. What do you mean by that? The OH group in the benzene ring, actually it ring activates towards the electrophile. That is, it allows an electrophile because it has electron rich centers. Because we studied the resonance, all these ortho para centers are having more number of electrons. So what happens? It allows the incoming group to attack my ortho and para center. That is how you get the reactions formed. First one is nitration. Phenol, when it is treated with just dilute means simply nitric acid, you get orthonitrophenol and paranitrophenol. But this orthonitrophenol is steam volatile. What do you mean by steam volatile? Vapors, it can immediately get converted into its vapor form because of the intramolecular hydrogen bonding. If you see, they can easily form a hydrogen bond between this hydrogen and oxygen. But here the hydrogen bonding is little bit difficult because the distance is more. This is also a board question. When phenol is reacted with dilute nitric acid, you get a mixture of ortho and paranitrophenol which is volatile. So ortho is volatile because of the intramolecular. What is intramolecular? Within the molecule there is a hydrogen bonding. So that's why orthonitrophenol is steam volatile than compared to paranitrophenol. Okay. But when the same phenol is reacted with concentrated nitric acid, you get both the ortho position and the para position being occupied by the nitro group. So you get picric acid, 1 mark question, 2,4,6 trinitrophenol. All the 3 positions are being attracted by the electrophile, that is NO2. So you get the formation of picric acid. Next is simple reaction, which is halogenation. So phenol, when it is treated with bromine at CS2, carbon disulfide, a solvent, you get minor product as the ortho, para will be the major product. Okay. But what happens here when you treat with just bromine water? There you used CS2. Here when you used 3 molecules of bromine water, you get again both the ortho and the para positions being occupied, which we call it as a 2,4,6 tribromophenol. Next one is a very important reaction, which is Kolb reaction. Again children, +1 we studied this, you remember? There we studied with RCOONA. Phenoxide ion generated by treating phenol with sodium hydroxide is more reactive towards the electrophilic substitution. So what is Kolb reaction? Very easy. Phenol with sodium hydroxide gets ONA. This we studied there, which when treated with carbon dioxide and H+, this bond breaks and you get hydrogen there and here you get COOH, which is salicylic acid. This salicylic acid is used for preparation of what? Aspirin. Remember acetylation. So phenol, when treated with sodium hydroxide, you get ONA, which when treated with carbon dioxide, you get salicylic acid. Very, very important. The next one is again Riemann-Tiemann reaction. Name reactions are all good to hear, difficult to learn, but I know my children will learn them, right? Now what is Riemann-Tiemann reaction? In Riemann-Tiemann reaction, phenol will be treated with chloroform. Very difficult to learn, I know children. Write and practice. Okay, you can do it. Phenol, when it is treated with chloroform, in the presence of aqueous base, you use sodium hydroxide. See what is happening very clearly. This sodium comes and attack my oxygen, hydrogen is removed, so you get ONA. Now what is left here? CHCl3. In this, one of the Cl comes out with hydrogen here, this hydrogen. So you get HCl and CHCl2. CHCl2, the Cl takes out this hydrogen and the sodium comes and attacks. So what you get is ONaCHCl2. Now this compound, when it is react with a base again, you get ONA the same position. Here oxygen comes and added, NaCl and HCl are removed. So you get a CHO aldehyde group. Now this on H plus treating with an acid, you get OH and this becomes CH2, same. Just ONA is getting hydrogen substituted. So which we call it as salicylaldehyde, an aldehyde compound in phenol, salicylaldehyde. If you have COOH here, salicylic acid. If you have an aldehyde here, salicylaldehyde. Next one is reaction of phenol with zinc dust. Very important. How do they ask this reaction is dash plus zinc gives benzene, or how do you prepare benzene from phenol? So phenol, when it is treated with zinc dust, you get benzene and zinc oxide. Easy reaction. The next one is oxidation of phenol. Phenol treated with sodium dichromate in presence of sulfuric acid, you get benzoquinone. Both the opposite position get oxidized with oxygen, so you get benzoquinone. Okay. So these are some of the reactions, and we have some important alcohols which are methanol. We have studied even in 10th standard children. You remember how methanol is prepared. Okay. So by destructive distillation, you just have to go through it. Learn 2-3 properties of methanol which are important. It can come in choice question. Ethanol, again in 10th standard we have learned fermentation process with invertase and zymase, the same set of reactions. Okay. So learn these two. Now with this our alcohols and phenols are getting over. Now we'll get back into ethers. Okay. Now let's see how ethers are prepared. The first preparation is by dehydration of alcohols. So what is happening here? Again dehydration is the removal of water molecules. So I have my phenol, or sorry, alcohol. This alcohol, when it is treated with sulfuric acid at 443, I get alkene. But same with sulfuric acid at 413, that is temperature little bit lower, I get my ether, C2H5O, C2H5. So understand the same reaction but giving different products when the temperature difference is little bit different. When you take the alcohol reacted with acid at high temperature, you get an alkene. Same thing at low temperature, you get an ether. Mechanism is not required for us. Next one is a very important name reaction, which is Williamson synthesis. See, this is a laboratory preparation of symmetrical and unsymmetrical ethers. In this, we take an alkyl halide, that is RX, it can be CH3Cl, which is treated with a sodium alkoxide. Now this can be C2H5 or butyl propyl, oxygen and sodium. So what happens here? Sodium takes out this halogen, comes out as NaCl or NaBr. Whatever is left is ROR dash. So that is how you prepare. If you have both of them the same alkyl groups, you get a symmetrical ether. If it is a different alkyl groups, you get an unsymmetrical ethers formed. Okay, see an example is given here where you get a tertiary alkoxide with a primary alkyl halide and you get a compound like this, right. So, better results are obtained if the alkyl halide is primary, if this is primary, and in case of secondary and tertiary, elimination is little bit, it competes over substitution. So, you get an unsaturated compound as your product like this instead of your regular product, that is ether. Phenol can also be used, where phenol, again the same method children, with sodium hydroxide you get ONA, which when treated with any alkyl halide you get OR attached here. So, the mechanism is the same, you just have to understand. Properties just go through. In chemical reactions you have the cleavage of CO bond. Most important reactions are ethers. When they react with HFs, you know what should happen? They give an alcohol, because when these two react, you get an ether. So, the reverse reaction is the property of ether. So, ethers on reactant with hydrogen halides, you get an alkyl halide and an alcohol, right. So, the order of reactivity will be HI greater than HBr than HCl. This just you have to go through it children. Next is most important electrophilic substitution reaction. With benzene or with phenol, you understood what is the method of resonance. Same thing happens here, they are more susceptible towards the electrophilic substitution, because this benzene ring, which is sp2 hybridized, it withdraws the electron from the oxygen having an unshared pair of electron. So, the ortho para position becomes more and more active for ring substitution. So, in halogenation we call this as anisole. This is an ether where C6H5OCH3. So, this anisole ether, when it reacts with bromine with ethanoic acid, you get para-bromo-anisole, ortho-bromo-anisole. OCH3 remains the same. Bromine gets substituted in my ortho and para position, which is my halogenation. Next is again Friedel-Crafts reaction, which we have studied already. Friedel-Crafts reaction takes place with alkyl halide and acyl halide, acid chloride, CH3Cl and CH3COCl, always in the presence of aluminium chloride and hydrous aluminium chloride, which we use it as a catalyst. So, this what happens when it reacts, you get a CH3 getting attacked here, hydrogen from here comes out as HCl. So, you get a ortho and para product. Similarly here, COCH3 comes and attacks, HCl comes out. So, you get again an ortho and para. 2-methoxy, this is 2-methoxy acetophenone. This becomes my major product. This is my main chain, this is my substituted product. Okay. Nitration. Nitration, always I have told you, you will have a combination of sulfuric acid and nitric acid. So, you get ortho nitro and here para nitro. Okay. Anisole. With only one you have to learn children. So, with this the reactions are getting over. So, what you need to do is, when you are studying this alcohols, phenols and ethers, put it in 3 different tabular column. Preparations you write for everything, chemical reactions you write, so that will be easy for you to learn without any confusions. So, learn the reactions by heart, definitely will be doing revision for you for your better understanding. Okay, with this chapter is getting over. Make sure that you practice it a lot children. Thank you, take care, bye.